Good morning, students. Today we are discussing about basic geotechnical engineering 18Cv54 module 2 lecture class through 3 soil structure, clay mineralogy and compaction of soil for 5th semester students. So the content of today's discussion is adsorbed water, base exchange capacity, isomorphic substitution, common clay mineral, kyanite, montmorillonitic and elatic clay mineral and engineering applications. Adsorbed water. What is meant by adsorbed water? A layer of water which is surrounding the clay crystal are called adsorbed water. If you take any clay soil, surrounding the clay soil there will be a thin water film take place. As I explained in the diffuse double layer, why that thin water film take place means the clay soil will have unbalanced negative charges. In order to balance itself to become stable, it attracts the positive charges H plus ion, and this layer is a thin water film layer, and this water is called as an adsorbed water. Base exchange capacity. What is meant by base exchange capacity? The surface atoms are predominantly negative charges or hydroxyl ions. The ability of clay particle to adsorb the ions on its surface or edges is called base exchange or cation exchange capacity. As I said earlier, so the clay soil will have unbalanced negative charges, so some charges will get attracted towards the positive, opposite charges attracted towards them, and it forms a stable compound. But if some more positive charge or opposite charge which is having a higher strength than the existing opposite charge which is present on the adsorbed water surface, then these charges will get releases from the base and the strong charges get deposited on the base, and this base level exchange of ions take place, and that is called as a base exchange capacity, where cations exchange take place. Therefore it is called as a cation exchange capacity. For example, if near factory or near seashore, any soil if you take it, that soil is rich in sodium, or any sewage which has passed through that soil, so that soil is rich in, that is, sodium concentration. So that soil is not at all good for construction purpose, because any soil which is having a sodium percentage more than 0.5% by weight of the soil, that soil loses its strength. So that ground we are calling it as a useless ground in terms of civil engineering point of view. But we cannot possible to leave that ground, because that ground may be in a very popular place, or it may be having a very good market value. Then we have to make that useless ground as a useful ground. How to do it? Next is you have to go for the ground improvement technique in general, or chemical stabilization in particular. So what we have to do? We have to identify what the chemical soil is contaminated. So once you know that chemical, you have to use an opposite strong chemical to remove the ions from its base. So or you have to remove the ions from its surface. So for that, for a sodium concentrated clay, if you had calcium chloride, then calcium reacted with that clay, sodium will be released, that is base exchange takes place. In place of sodium, exchange of ion take place by calcium, so that calcium will replaces the sodium place, whereas the sodium will mix it with the chloride ions of calcium chloride, it forms NaCl, sodium chloride, and the soil becomes calcium clay. As we know that calcium is very good, and if in presence of water, calcium hydrate reaction take place, and it increases the bearing capacity. Thereby useless soil will converted into a useful soil of very high bearing capacity. So for this type of ground improvement technique, we are using base exchange capacity. So coming to the mineral, for the engineering point of view, clay minerals are classified into 3 types: kyanite, montmorillonite and elatic clay mineral. So kyanite means, so if you see gibbsite sheet and silica sheet is bonded together. One gibbsite sheet is a rectangle in nature, one silica sheet is a trapezoidal in nature. So they are perfect bonding with each other, and whose thickness is 7.2 angstrom thickness. And again the silica sheet get bonded with the gap side sheet. That means the opposite charges bonding take place. Therefore there is no gap of exchangeable ions. Therefore water will not enter into that one. Hence that type of clay minerals are very strong clay minerals, and the swell shrink capacity is almost zero. Coming to the next type of clay minerals, Piedmont monolithic clay minerals. So this type of clay minerals where one gibbsite rectangular unit gets sandwiched between two silica units trapezoidal in nature. It forms a one unit, that is 9.6 angstrom. Again second 9.6 angstrom will also have silica, that is gibbsite is sandwiched between two silica units. That means the outer surface of each unit is exposed to silica, that is the units. So two such a units come in close together, there is a silica that is a repulsion take place, and that gap has been filled by the water. As water is a weak secondary bond, exchangeable ions will be there. Therefore during emergency it absorbs water, during some other ions comes, it releases the water, so the base exchange capacity takes place, which leads to swell shrink behavior. Coming to the third category of engineering point of view clay mineral is elytic clay mineral. Elytic clay mineral will also contain a gibbsite sheet sandwiched between silica sheets. So each unit will be 9.6 angstrom, 10 angstrom thickness. Between the two units, so of the elite, so there will be a repulsion between the silica there, but there is an isomorphic substitution between the two units by potassium. That potassium will somehow balance the repulsive, or reduces the repulsive power, increases some extent attractive power, but that bonding strength is weaker than kyanite but stronger than montmorillonite. Therefore in terms of swell shrink behavior, it is less swelling compared to montmorillonite and more swelling compared to kyanitic group. Coming to the MCQ questions, first one is two fundamental building blocks of clay minerals are tetrahedral unit option A, option B octahedral gibbsite unit, option C both A and B, option D is none of the above. So option C both A and B. Engineering point of view, clay minerals are classified into dash type, option A 1, option 2 B 2, option C 3, option D 4. Answer is option C 3. The unit thickness of kyanite is dash angstrom, option A 7.2, option B 9.6, option C 10, option D none of the above. Answer is A 7.2. The unit thickness of montmorillonite is dash angstrom, option A 7.2, option B is 9.6, option C is 10, option D is none of the above. So your option is 9.6. B. The unit thickness of elite is dash angstrom, option A is 7.2, option B is 9.6, option C is 10, option D is none of the above, option C it is 10. Next, fundamental building blocks of clay minerals, option A true, option B false. So there is false, 3 fundamental building blocks of clay minerals are there. So next, all clay soil is problematic in nature. So option A is true, option B is false. No, it is false. All the clay minerals are not problematic in nature. For example, kyanite is a clay mineral. It is not problematic in nature at all. Swell shrink behavior of clay is because of unbalanced surface negative charge. Option A is true, option B is false. It is true. A. Uplift pressure is expected in BC soil. Option A is true, option B is false. It is true. A. Option A. BC soil is highly permeable. Option A is true, option B is false. It is false. So thank you for attending the class. You please go through the MCQ questions once again. If you have any doubt, we will discuss it in the next class.